Now, this top paragraph, it's explaining how pressure waves can travel through a pipe. But rather than me just repeating what's on that paragraph, have a quick read. There's a very good set of websites called UNSW, physics.unsw. And they have heaps of useful websites on sound and acoustics. The links are at the top of the relevant pages. But what's important is the animation down here. Now, this is showing how pressure waves are reflected in a pipe. So follow the pressure wave. You'll notice that when it comes back, it's changed. When this pressure wave travels out, the pipe is generally at 1 atmosphere. There's not much of a pressure differential unless we just make some kind of disturbance by blowing air across or having a reed or a speaker or some kind of driving source. When this pressure wave travels out, it expands out into the atmosphere. And as it expands out into the open atmosphere, because it's no longer constricted to the walls of the cylinder, we model this as a simple cylinder. We assume that the pressure wave travels perpendicular to the walls, parallel to the line. When it expands out, what it does is it creates behind it an area of low pressure, and it's actually the low pressure wave that's reflected back into the tube. So have a think. We have a crest travelling out. The crest might represent a high pressure. It's reflected back into the tube as a trough. Well, that's very similar. Did I not say, and don't lock it? Did you? I thought we'd gone beyond that. Why would you lock the door? When the low pressure returns, on the way out, as the rarefaction enters the outside atmosphere literally collapses in due to the atmospheric pressure, and then it's that high pressure of the atmosphere collapsing back in that reflects it back as a trough. So think back to a pulse on a string. We have trough reflecting as crest, reflecting as trough, reflecting as crest. All we need to do is make sure that we can drive that at the same frequency. Now, rather than this wave speed being that of a string, which is determined by the square root of t over mu, the wave speed is just the speed of air, which is dependent on temperature, but let's just say it's 346. So now we can set up exactly the same equation, that the time it would take for the pulse to travel back to where it started would be 2L on V, or V on 2L. I always get that wrong. S equals VT, T E S divided 2L on V. Okay, so the frequency simply needs to be V on 2L, right? So if I just had a frequency of V on 2L, I could set up the first harmonic. If I doubled the frequency and sent another pulse now, they would meet in the middle. They would cancel, yeah? So I could set up the second harmonic. If I doubled the frequency and went 2V on 2L, so boom, 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 double the frequency, we should be able to set up another standing wave, the second harmonic. Or then the third, and then the fourth. The equation is identical. What I would like to show you over here is an open-ended tube, right? Now, we'll treat that in this room right now, let's just do a nice round 340. The speed of sound is 340. The length of this tube is 1.3. So the fundamental frequency should be 340 on 2.6. Go on, Cameron. This is your moment.
I think I'll just keep this to myself.
Just a guess.
900, 880.
113-ish. 118.
88.4.
No, I'm just keeping some to myself. 130.7.
About 130. Okay. Now, guys, this is not being amplified. This is just the noise of the speaker and the tube might be vibrating slightly, but if we eventually get up to... We went past it. That, 109, all right? Maybe my maths was wrong. 109.
What's happening?
That's the fundamental frequency. So basically pushing a kid on a swing, or your metal plate driving at just the right frequency that we've set up the fundamental. Now let's double that.
Is the reason your voice sounds
if we
weird
went
with
to
frequency?
if we went to double the frequency, about 220-ish for this, we should be able to see that the volume's gone back down. They're reflecting, but they're not in harmony. They're not working together. It's like pushing the kid at the wrong time or making the string not in harmony. Let's keep going. All right, second harmonic. Let's go to the third. Right? I'm not changing the volume of the speaker. I'm just changing the frequency. So about, what, 360-ish. Now let's go to the fourth. About 480. And now to the fifth.
Could you then reverse interpret
Alright.
the speed of sound?
Alright, so we were just doing the whole pushing the kid at the right time. Alright, the second harmonic will be pushing the kid here, and then another person pushing there, and then another person pushing here. The third harmonic, the analogy breaks down because there's only two ends to a swing. Yes?
So are harmonics just frequencies where the amplitudes really matter?
Frequencies where pressure waves are allowed to constructively interfere with each other to produce large amplitudes, large pressures, and hence large sounds. Okay? Now, there is a YouTube video that we will watch at the end. I can't play it or I'll get flagged for copyright. So could we now go to the fun part of the video? Now,
Copyright strike, Mr. Ryan.
Gents, please stop talking. We're going to sketch two different kinds of variations in these. You have to be able to sketch these. Could we please draw the particle envelope? I start with what the particles are doing. Now, the particle envelope says that we have maximum air displacement at the open end. That is the rule for the open end of the pipe. You will have an antinode at each end. Now, when we're talking particles, we're talking about how far they can move. It's very similar to the string. When we had an antinode in the middle, the string was moving at its maximum displacement of the string. We had a node at the end of the string. So, okay, maybe our particle envelope of the open pipe is kind of the opposite to the particle envelope of a string. What we then need to have is a node in the middle. So you need to sketch half of a wavelength.
Measure.
All right. Now, just like the string, I'd like you to draw a dashed line on the other side, and that dashed line will sort of tell you the range of the displacements. Okay? Now, same as the string, and this is the lesson that I asked you to watch over the weekend. The names, you've got to be careful with the names here. We've got the fundamental, which is also known as the first harmonic. You need to be careful as to what you've been given. You could be given either of the naming techniques. You could be asked for the second overtone or the third harmonic. They mean slightly different things. Just for fun, we'll write that the wavelength is going to be 2L on 1. We have derived the equation anyway, so there shouldn't be any surprise. F1 equals 1V over 2L. And this is obviously, N equals 1. Now, it's going to be a bit boring, but we're going to do exactly the same. But, hang on, I need to label my node in the middle. Now, sketching this is a little bit tricky. We're going to have to put an antinode in the middle now. So we'll have an antinode here, an antinode there, And equally spaced between our antinodes are going to be our node points, where technically, if you watch the particle, it wouldn't be moving because you would have a pressure wave arriving at the same time as another pressure wave reflecting. And if the two pressure waves meet, they want to push the particles, but they're trying to push them in opposite directions, so they work against each other. So anyway, let's sketch what we've got here. This is just a weird way of drawing a wavelength. We don't tend to draw a wavelength like that. Oh, I'm going to try this one last time. There we go, that'll do. But that is one completed wave. We just tend not to draw it in that kind of way. Because the rule is that the end of the pipe must be a particle antinode. The particle antinode is a position of maximum particle displacement. If we could watch one particle at the end of the pipe, we would see it move way out as the pressure wave travels through, and then it gets sucked back in by the rarefaction. And so you've got your particles are traveling the most at the end. Directly in the middle, you would see a particle basically being pushed from both. It would not move. Technically, those molecules would remain stationary, aside from random temperature movement. Okay, next. This is now called the first overtone or the second harmonic. And this corresponds to n equals 2. We have lambda 2 equals 2L on 2. Yep, that makes sense. The wavelength is the length of the tube. And F2 equals 2V over 2L. Let us keep going so that you can solidify this into your head. We need an antinode here, an antinode there, and now we need two antinodes equally spaced. So we're going to have 3 nodes right now. So now we're going to draw 3.5 wavelengths. And I always forget to label your nodes, which is where the particles are not moving.
Line's kind of a representation of how far the particles move.
Yeah, if we could turn this into an XY axis, where Y is now, call the Y axis the range of motion of your particles. And you would see at an antinode you have the maximum range of motion in both directions, positive and negative. All right, second overtone is what we call this, which is our third harmonic, n equals 3. We might as well just go all the way. Let's complete all of the equations. Lambda 3 equals 2L on 3. F of 3 equals 3V over 2L. Let's keep going. The main trick here is to figure out, in this case, it's the number of nodes. You could count the nodes and that's going to give you I don't want you to remember that because we've got a different wave envelope that we're going to sketch in just a moment. You really just have to go, well, our first harmonic would be that, our second would be there, our third would be there. We need to produce 3 evenly spaced antinodes in between, with a node, with a node, with a node, and then you're basically just drawing a sine wave through those nodes. And really, you're not going to go much further than, say, n equals 4 or 5. It would be very cruel to ask a student to sketch the particle envelope of the 11th harmonic, because then you'd be sitting there trying to draw 11 nodes and 12 antinodes all equally spaced. It'd be a bit cruel.
So it'll be an answer.
As I said, you probably would not be asked to go beyond n equals 4 or 5. The third overtone is the fourth harmonic with an n value of 4. So let's recall our tricks of the trade. F of n equals nv over 2l, or n times the fundamental. Recall, if you find the fundamental, you just can multiply. I mean, you guys were doing that in your strings prac yesterday. I was doing it just then. You find the fundamental, you know that every successive overtone is just a multiple of that. Okay? Now, on this bottom graph, there is one last trick that we are going to use, and it might pop up in some tricky exam questions. Could you just draw from antinode to antinode? We're going to call this length the internodal distance.
1/2 wave.
Yeah, but you've already gone ahead and copied the... The internodal distance is half of a wavelength.
That was very hard.
It's a little trick that we can use if we are unable to measure the first length. There's a prac that we might do after the test in that week where we're not allowed to assess you. We might set up a pipe demo where we can show you this. You can vary the length of a pipe by having water filled in it. And then you can change the length very easily. Anywho, this was all about particles. And my preference when sketching, I always start with what the particles are able to do, and that can then determine how I sketch my envelope. Again, this is showing the range of motion of the particle. So the particle is literally going in and out by the most. Have a think. At the particle node, you might have a... Now here, Emil, put your hand down. You can get a sore shoulder. My fingers are going to represent the pulse travelling through. Moving that way... Sorry. Moving this way is a pressure wave. All right, so here I have two pressure waves. If the pressure waves meet, they want to push the particles in the direction that my fingers are pointing. So in the middle of the pipe, let's go back up to that example there. In the middle of the pipe, we've got two pressure waves meeting in the middle, and they're both exerting equal and opposite forces on that molecule, particles. The particle doesn't move. We would say that the pressure waves are working against each other. We're going to call that a pressure antinode. But if I looked at this scenario, I could have a pressure wave at the same time that this is now a rarefaction, right? So this is a rarefaction, low pressure, wants to suck the particle in. No, please stop talking. Thanks. You've got a pressure wave and a rarefaction wave advancing at the same point. This particle is going to be moving because the pressure wave pushes it to your right and the rarefaction pulls it to the right. So if they can both meet in the middle, we would have a particle antinode, which would be a pressure node. If they're working together, we can call it a pressure node. Let's just go to the outside. The particle antinode would be a pressure node. So that's going to be, imagine a pressure wave's traveling out at the same time a rarefaction wave is moving in. So just as that pressure wave pushes that particle out, the rarefaction wave sucks it out as well. So you're pushing it to your left and you're pulling it to your left. So you're going to have a particle antinode produced by a pressure node where they're working together. When pressure waves work together, we can get maximum movement. What I was trying to explain is this diagram over the page. Now, I have borrowed this diagram from an old textbook, but it basically has everything. What I asked you to sketch on the previous page was the particle displacement. We've got the naming here as well. All right, so I can't remember what my colouring was, so the fourth harmonic was green. I might just maintain the same colour coding here. And then the fundamental, first, second, third, and fourth. So, please remember, and this is how I remember it. If I was asked to draw a pressure wave, I just go, hang on, what are the particles doing at the end of the pipe? That's right, they're moving the most. So if a particle antinode, we must have a pressure node at the end, okay? So you just be careful as to what you will be asked to draw various envelopes for various scenarios. Strings, open pipes, or closed pipes. We will do closed pipes in tomorrow's lesson. Yes, Emil?
So what's a particle envelope?
A particle envelope is basically a sketch that shows you the maximum range of motion. I think Sam was asking about it. Imagine I went to, don't draw this, but imagine I placed an XY axis. Not supported. Along here.
So you know there's an XY axis.
And this graph now might represent the X displacement along the length of the tube. So an antinode basically means this particle is going to move the most at the end. But it's, okay, so I've got a vertical axis, but really it's representing the horizontal motion in and out of the tube. If I went to this point here, you would find that there is less, we're still on ink to shape, go away. We're getting less and less motion of the particles. And then it builds again, and in the middle we get the most motion, and then it drops, and then we get a node. So again, if we could represent the horizontal motion, we would sort of get this envelope. All right, I'm not drawing it very well, but you would get that envelope.
Is that because of the interference that it varies?
That is because of the pressure waves that are traveling through the pipe and being reflected through the pipe are interacting with each other, just as waves do. The regions where they're working together, we see maximum particle displacement. The regions where they're working against each other, we see zero. So air pressure or pulses on the strings, it's exactly the same. You could replace the word air pressure with transverse displacement of a string. Whereas this is longitudinal, right? What we did yesterday was a transverse wave. These are longitudinal waves, but they can both be represented by the same curves. Let me just redraw this to get rid of all of my... Well, over the page... Do you want to draw pressure? You can. Yeah, they're envelopes.
Or the left one is an envelope.
No, the right ones, yes.
They're both envelopes. They're a representation of the amplitude of the superposition of waves. So what you find is either pressure or displacement on a string is within those boundaries. And those boundaries just happen to take the form of a sine wave. Okay? Yes, Minchin.
Two things. How do you measure the displacement of a particle against its...
Yeah, you're right. Literally, the particles are not moving
along the axis you're measuring it.
The particles themselves aren't moving much. So as I'm talking, or when we had the pipe going there, you might be talking millimeters of movement, lateral, longitudinal movement. But you've got so many molecules traveling at such a speed that we can get that sound energy reflecting backwards and forwards. But that reflection can only work dependent on how fast that pressure wave moves. It's also dependent on the length of the pipe, and then finally it's dependent on the harmonic that we can establish. Okay? Could you just rewrite this? No, you got one. That was all.
I did ask for two.
Okay. Just have a look at your pan pipes. They are a good example, or a glockenspiel. David Jones, was he at the chapel last week with the glockenspiel out the front? They're an example of an open-ended pipe. You strike the open end, you send a pressure wave through it. Okay? Marimba, glockenspiels, pan pipes, the organs in the chapel, they're all going to be open-ended pipes. If you are not, can you please stop talking? It is rude. If you have a question, raise your hand. Thank you. I've given you the wave speed. If you are not given the wave speed, you have to use the value that's given in the data sheet. Okay? So sometimes we force you to use 342 or 341. If there is no mention, then you have it provided in your physical data on page 3. It says down there 346. So that's the speed of air when the temperature is 25 degrees Celsius. On a cold day, it's slightly slower, and on a hot day, it's slightly faster. Okay? Now, could you please use this information that I have provided The first harmonic is prompting you that n equals 1. We've got V. We need the range of frequencies. So that it's F1 and F1, but obviously we've got L and L. So just split this page into 2. You're using exactly the same equation, but your lengths are going to vary from 0.15 through to 0.50.
It says the first harmonic. Does that mean that all pipes will be different?
Okay, I'll show you a cool trick. You can establish higher harmonics by blowing faster air across. But typically, I'm not going to be able to do it with this, but
I understand.
typically it's drawing air in. I'll show you in a moment. Do these two sums for me. I'm just going to get one more device that we might be able to look at.
Mate, that thing we just looked at made no sense.
When it was just like pressure waves, I was like, but you can't ask
Did
me.
did anyone understand that?
The pressure variations is a normal thing.
No, I got to ask the explain the same side.
just did accept.
No, I got.
Yeah,
Yeah,
but
yeah.
it's just a class where I just accept. Like,
No,
just
I
don't
understand.
It's okay.
Which is fine.
Contaminated.
So what is N?
N is the number of the harmonic. You might wish to, since you've asked a very integral question, you might want to write n equals 1, n equals 2, n equals 3, n equals 4, n equals 5 along this table. First harmonic.
So is it always?
You might want to write n equals 1 here. Do it. Do it. Do it. Right? Yeah. Now, see how it says first harmonic? You can come up to this table and go, oh look, the first harmonic is n equals 1.
Is there a 0th harmonic?
There is not a 0th harmonic, no.
Would a panpiper create a second harmonic?
You can allow me to introduce to you the song of my people. Now this is a closed-end pipe, but I can do first harmonic, right? Third harmonic. Not
Really?
this. Yeah. You can go further up. Now I might be able to go one higher. Hang on.
Oh yeah, true.
All right.
That's
By,
it.
by blowing air at a greater speed, you can generate higher harmonics.
With the second.
So this one was. You can go further down.
Is that
You keep going?
So,
that
can you please get like different size test tubes and just go?
Yeah, do a hillbilly too.
I'm glad you asked.
Oh yes.
Oh wait, hang on. Oh, this got a crisper sound.
Jesus.
See how they're all sounding the same?
Put them all together.
It's the length. The length of this tube determines the frequency from this equation. Even though they've got different
It's
diameters,
still the same.
That's
the diameter doesn't change the rate at which my
Yeah,
pressure
yeah.
wave reflects back to the top.
Cross section.
This one, however, is a little bit smaller, so smaller length.
Go nuts. Go nuts.
So it makes them fine.
Hang on. If I reduce L, my frequency would go up. And that's what that panpipe question is showing you. You should notice that the smaller length had a higher frequency.
Whoa.
Go, go, go.
There is a class next door and I'm starting to get a bit dizzy, so we'll stop there. This is a closed pipe, so this will make more sense tomorrow. Did we get the questions done? The second equation you might have noticed was a little bit easier because we got 1 by 346 over 2 lots of a half. So that would just be 346 hertz.
The other one's 1,100.
Say that in about 2 seconds.
1,150.
That was closer to 4 seconds, but you got that's fine. We're good. We're good. Okay.
buddy.
All right. We've got 10 minutes left. Now, if you want to impress people.
This is the Miss Mariah party trick.
Alright.
So
A student did this about 3 years ago, and I was like, what? It must have been a muso. Basically, this tube, we've locked in the wave speed, we've locked in the length. What I might do, okay, let's do some estimations, right? A 1 meter pipe, 346. So what would the fundamental frequency be? It would be 1 by 346 divided by 2 lots of 1. So 346 on 2. It should be around about 170 hertz. Right? So if I took it up to that speaker and set it to 170 hertz, we should be able to hear a loud resonant harmonic. If I increase, it goes low. If I get to the next harmonic frequency, it might come loud again. So you can do things. I hope this works.
Auto-tune?
Huh?
Oh, wow. Oh, sick.
Are you just blowing in?
I'm just going
He's whistling, but it's auto-tuning.
like a siren.
Do it again.
Here's,
I'm gonna spit some fat
Wait,
bars.
so
I've already been slobbering on one end. Give it a go.
I can
Get my
use
auto-tune
auto-tune.
popping.
Are you blowing in or blowing out?
It's easier if you blow air in. He's got it.
Sound.
Yo, I'm spitting bars.
So you changed
I can't do
It's
it.
like
No.
auto-tune.
Oh yeah, I'm
I'm sick, don't do it.
like a siren, right?
Do it again.
No, I don't think
Even closer.
What's the difference?
I'm not doing the auto tuning. This is literally amplifying the harmonics.
Go again,
It's-
go again.
Why is it auto-tuning?
Shush, shush,
so.
shush.
Lil News.
Hang on.
Everyone shut up, everyone shut up. Whoa.
It's almost doing, what do you call it in music?
Octave
scale.
Scales. It's doing scales.
Why?
It's just selecting the frequencies that it can resonate
But
at.
it's selecting like 20 different frequencies.
As I'm going,
So it's resonating.
it's just it's resonating at the frequencies that.
It seems like it's finding like
Yeah,
seven, like 10. So it's finding like 10 different harmonics in that.
Well, here's the thing. Here's the thing. Your frequency might have gone through. Well, I'm not sure what the frequency. What did we say? It was 170 hertz. It would have gone through a certain interval of frequencies where it was allowed to resonate at. Okay, that's enough of that.
YouTube video. So.
There is a year 7 class next door, so
That'd be loving it. Do you reckon they can hear us?
That'd be like spirits.
you can do it in 9 minutes time. We'll stop the video here.